All right, guys. So on the right side of the board here on this side, I'm going to sketch the graph for fx equals 1 by 2 raised to the exponent x. Okay, so this is going to be the graph for fx 1 by 2 raised to the exponent x. All right, so now you can see here on the left side I have done it for 2 raised to the exponent x. So here I'm going to take the value of a between 0 and 1, right? Okay, so let's get started. So if we put value of x0 here, it's going to be 1. So I have told you this point is very, very important, no matter what is your base. So if you sketch the graph exponent, if you sketch the graph of the exponent function, so it will always pass through the y-intercept 1. Okay, so if you put a value of x1, so here it's going to be 1 by 2, right? 1 by 2. If you put value of x2, it's going to be 1 by 4. If you put x3, value of y is going to be 1 by 8, x4, 1 by 16, x5, 1 by 32. Okay, I hope you understand it. Okay, I did nothing. What I did, I just put in the different values of x, and then I've calculated values of y. Okay, same here. Here, if I put value of value of x minus 1, so 1 by 2 minus 1 minus 1. Okay, so it's going to be 2, right? So if you put this one 1 by, it's 1 by 1 by 2 minus 2, right? So it's going to be 4, because we are just doing the reciprocals, because the exponent is negative, and to make it positive we need to do the reciprocal. Okay, same goes here for x minus 3. So your value of y is going to be 8. For minus 4, 16. For minus 5, 32. Okay, now see here, when we did the graph for a raised to the exponent x, or 2 raised to the exponent x, the same values we got on the on the on the right side. And if you look at this graph, you can see the same values of y we are getting on the left side, and the values that we get for this graph on the left side, you can see here we have the same values on the right side. Okay, so what does it mean? It means this graph 1 by 2 raised to the exponent x, this graph is going to be the reflection of this graph around here y-axis. Okay, so if you plot minus 1 2 minus 1 2, this one here 2, then minus 2 4 minus 2 4 4, and then minus 3, sorry, minus 3 8 minus 3 8 somewhere here. Okay, so this is going to be like, this is what, if you trace all the points, it's going to be like, it's going to be like this. Okay, it's going to be like this. So it's going to be like this. Now, now we have to compare these two graphs and see what can we get out from both of these graphs. Okay, so if you look at this graph, you can see here, as the value of x increases, y increases to, and at some point here, after 1, this thing is going to just skyrocket, right? Okay, so it means that a raised to the exponent x, it shows the graph of, it shows growth. Okay, it shows growth. Okay, because as the x increases, y increases exponentially, right? So this is the graph of growth. But here you see that when your x is increasing, your y is decreasing, okay? Decreasing, and this is the graph of decay. Okay, so when we speak about exponential growth, it means we are talking about this thing, and when we speak about exponential decay, we talk about this thing. Why? Because see here, this side, the graph, the value of y is approaching towards infinity. And if you go to the other side of this curve, then you can see that your horizontal asymptote, it is approaching more towards 1, sorry, more towards 0, but not, it will never become 0. Okay, so this horizontal asymptote, the value is 0 positive, means not exactly 0, but little greater than 0. Okay, so this horizontal asymptote, it's going to, it will tend towards 0, but it will not become 0. Here same, when this starts, so this starts with the horizontal asymptote that tends towards the 0, and then as the time passes, then it just skyrockets. Okay, so this shows growth, this shows decay. Okay, now if you see the graph of ax and 1 by ax, okay, so here I can write, this is growth, this is decay, and I can say, okay, ax, okay, ax and 1 by ax, these are going to be reflection. Okay, these are going to be the reflection of each other. Okay, these are going to be the reflection of each other. Okay, cool. I hope these points are clear. Okay, now here I want to talk about one more thing here. Sometimes what happens is that they may ask you to shift the y-intercept or horizontal asymptote. What does it mean? For example, this shows the graph of 2 raised to the exponent x. Maybe they ask you to sketch the graph for 2 raised to the exponent x plus 2. Okay, so you have to sketch graph for this. Okay, now see here. Now, what happened is, your for 2 raised to the exponent x, your y-intercept, it was made at y equals 1, right? But now see here, to shift y-intercept, okay, to shift y-intercept according to this, so we have to shift our y-intercept 2 steps up. Okay, so this is going to be the first step, this is going to be the second step. Okay, so it's going to be here. So new y-intercept, it's going to be formed at 3. Understand? So and the horizontal asymptote, because y-intercept is at 3, so the horizontal asymptote is going to be formed at 2. Okay, so your graph will be something like this. Okay, uh, this is going to be your horizontal asymptote. Okay, so this is going to be your horizontal asymptote, and then uh, it will follow this way. Okay, so this blue curve is the graph of 2 raised to the exponent x plus 2. Okay, so this part of the graph that tends towards 0 but not really 0 is known as the horizontal asymptote. Okay, horizontal asymptote. This is your horizontal asymptote. Okay, horizontal asymptote. Okay, so there is no problem. Sometimes they can shift the y-intercept, no problem. Okay, so for example, if it is 4 here, so it will go 4 units up. Okay, or it will shift 4 units up. Okay, so 1 2 3 4, so y-intercept is going to be at 5, and your horizontal asymptote is going to be formed here at 4. Okay, close to x equals 4, right? Not x equals 4, but y equals, uh, yeah, y equals 4. Okay, so you have to understand this thing. This is very important. Okay, now I hope you understand it. Now let's go. Same here. Here too. If they say that, okay, you have to do it for plus 2. Okay, so just move it 2 steps up. Okay, if you move it 2 steps up, then what would happen? It's going to be 2 steps up, 2 3, so it will pass through 3. Mm, this one. Okay, this is going to be, okay, this is going to be fx equals 1 by 2 raised to the exponent plus 2, because your y-intercept is shifted 2 units up, and then horizontal asymptote is going to be formed here. Okay, so pretty easy. I hope you got it. Okay, because we did the same thing when we studied absolute value function. Okay, all right, so now let's discuss few more things, important things, and then we'll close this session. Okay, uh, so now come to the basic definition, come to the complete definition of our exponential functions. Okay, so we said that uh, these the exponential function must follow this condition. Okay, so let's see, what if it says that a must be greater than 0 and a is not equal to 1. Let's see what happens if we put a equals to 0. Okay, so my first case is case 1, when a is equal to 0. Okay, a is equal to 0. When your a is equal to 0, then what would happen? F of x would be 0 raised to the exponent x, right? 0 raised to the exponent x. Now see here, when 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 x is negative, okay, when x is negative, then what would happen? Okay, fx is equal to 0 minus x, so I have to do 1 by 0x, which is 1 by 0. And what is it? This is the biggest blunder. Okay, this is the blunder in math. Okay, so just to avoid this, there we have to declare, or we have to make the condition while defining exponential functions that a cannot be 0. Okay, I hope you get it. Okay, now let's see if a is case 2, case 2, when when a is 1, right? A is 1, because it says a should not be 1, it must not be 1, but we want to see what would happen. Okay, so if a is 1, then your fx is going to be 1 raised to exponent x, and it's going to be 1, right? It's going to be 1. So what is it? This is a constant function, right? This is the constant function. Okay, so if you will make the graph for this, okay, so you will get the horizontal line. Okay, this is your y equals 1 horizontal line. So what does it mean? It means that this is not your exponential function, or this graph doesn't follow the sketch of your exponential growth or the exponential decay. It's just a horizontal line which says that this function is a constant function. Therefore a must not be 1. Okay, I hope this thing is clear to you. Okay, we can take one more case number 3. What's that? When a is negative. Okay, so when a is a negative. Okay, so what happened when a is negative? So your fx is going to be minus a raised to the exponent x, right? Now let's take an example. If fx is minus 2 raised to the exponent x, then what would happen? F of 1 would be minus 2, f of 2 would be 4, f of 3 would be minus 8, f of 4 would be 16. Now you can see here, as your x is increasing, what's happening? The value of y for one point on x-axis it's negative, then next point it's positive. Okay, so it's just like that. The values are oscillating. Okay, the values are oscillating. So when you get this graph of oscillation, then it does not represent exponential function, because exponential means that your graph must skyrocket as you increase the value of x, or when you decrease the value of x, right? So this case is not valid. Okay, it is a valid function, but it is not the exponential function. Okay, this is also a valid function, but it is not the exponential function. Okay, but this is invalid function. Why? Because here you get the biggest problem, right? Okay, so that's why we don't consider these 3 things when we define our exponential functions. Okay, I hope you have a crystal clear picture of exponential functions, and in the coming lectures we will switch over to logarithmic functions. Okay, so have a great time. Bye bye.